Hi guys, week 4, part 2. This is where it starts getting gnarly. This is our review for benchmark number 7, which is the final benchmark for the whole year. And blessing and a curse, I would say. A blessing because it reviews and goes over everything we've done this year. Curse would be there's 48 problems. But it really is a good thing. I'd like to challenge you to see which ones can you do without watching the video. The packet or the PDF does include an answer key and a step-by-step guide. And of course, you can watch this video, but see where you're at, see what you remember. And if you don't remember things, watch this video over and over. Practice it on your own because I do want you to be confident going into high school. Okay, so here we are, week of May 4th to May 8th. Do the Test 7 review. You're going to have the benchmark Test 7 next week, and we'll go through that whole thing as well. And this is review to prepare you for that. Okay, if you prefer, here's multiplication table, division table, and we are going to start out with some geometry. And I keep having these like massive headaches after these videos, and I've said it multiple times. I keep reading my glasses. I got them. Woohoo! Okay, so what are the values of x and y? Well, I know that in a triangle, the sum of the three angles has to be 180 degrees. So let's look at this triangle here that has x in it first. And so we're just going to add them up. So x plus 25 is going to be this angle here. So we'll go x plus 25 plus, over here is 35. And this right angle up here, of course, is 90 degrees. And all of that equals 180. So now we just solve for x. If we were to add these three together, 25 plus 35 is 60. 60 plus 90 is 150. So x plus 150 equals 180. We're going to subtract 150 from each side. That lets me know that x is 30 degrees. Okay, so we have x equals 30 degrees. And so now we needed to do we need to do the same thing for angle y. Okay, so that is over here. And I am just going to keep writing because look how cool this is. So x plus 35 is whatever this angle is here. Okay, so it's going to end up being the same thing except y. So we have a y. Put it here, plus 35. Oh, here it is, plus 35, plus 25, plus this triangle has a right angle also, and all of that equals 180. It's the same other degrees, each of these, so it's going to be the same thing. All I have to do is substitute in y. Y also equals 30 degrees. Oops, there we go, delete. And next problem. Okay, so on this one here, you'll see that I enlarged this picture right here. These are for numbers 2, 3, and 4. So right here, this is number 2. This is number 3. And this is number 4. Okay, so it says two parallel lines are cut by a transversal as shown. So here's our two parallel lines. These are parallel. And parallel lines, they go on forever and they never intersect. That's what makes them parallel. And that gives them a special relationship with this transversal line. Okay, so let's see what we are looking at. So it says if the measure, that's what M means, if the measure of angle 6 is 43 degrees, so 6 is 43, what is the measure of angle 2? And what is the measure of angle 4? What is the angle of measure 3? Okay, so when we're looking at this to angle 2, you'll notice that these are, so here is 6 and here is 2. Oh, that makes it confusing with that color. Let's change it here. So with angle 6 and with angle 2, these are called corresponding angles. And that's because they are in the same spot on their lines with the transversal line. So that means that angle 6 is the same as angle 2. So angle 2 is 43 degrees. Okay, that one was for number 2. Problem number 2. Okay, so now we're going to look at number 3, and it's asking about angle 4. Okay, so from angle 6 to angle 4, these are alternate interior angles. Okay, and here's what's really cool. Alternate interior angles are also equal. So angle 4 is also 43 degrees. Okay, and that was for problem number 3. I'm going to do it this way. Let's see, it's 43 degrees. Angle 2, 43 degrees. Okay, now we have measure 3. And here is where 3 is. And so this is going to be the same side interior angles. And so that means that the measure of angle 6 plus the measure of angle 3 is going to equal 180 degrees. I should have done that one in a different color also. All right, so let's see here. We know angle 6 is 43. So that plus whatever angle 3 is going to equal 180. Subtract 43 from both sides. Then we have angle 3 is, and I'm just going to use my calculator, 180 minus 43 equals 137 degrees, and that's for number 4. Okay, and we can write that here, 137 degrees. Okay. Number 5. Okay, triangle ABC has side lengths of 6, 8, and 12. Is it a right triangle? Well, I know that for a triangle to be a right triangle, it means that one of the angles is 90 degrees, that you can use Pythagorean theorem. So a squared plus b squared equals c squared. So let's plug them in. I know that C has to be the longest one because that is the hypotenuse. Okay, so let's plug in our values. 6 squared plus 8 squared equals 12 squared. 6 times 6 is 36 plus 64. Does that equal 144? And I can look at 36 plus 64. 6 plus 4 is 10. Carry your 1, that gives you 100. Does not equal 144. So it's just a regular triangle. It is not a right triangle. So it says, is this a right triangle? And the answer is no. All right, number 6. If a right triangle has a hypotenuse of 10, let's draw our right triangle. Hypotenuse is the long one, hypotenuse of 10. What integer values could the two legs have? So that's just saying, what could A be and what could B equal? Okay, so 10, I don't know, we did 6 and 8 on the last one. Let's give it another try. Pythagorean, a squared plus b squared equals c squared. So I said, let's give 6. Oh, that's a squared. Plus 8 squared. Does that equal 10 squared? And yes, it sure does. 6 squared is 36 plus 64. And yes, we just said that that does equal 100. So that lets us know A equals 6 and B equals 8. So when it says what integer values, what numbers are they? It's number 6. Okay, number 7. What is the value of x? So x is actually c. We're still with Pythagorean. I'll tell you what, there are many things that I have forgotten as I've gotten older, but I have never forgotten Pythagorean. Pythagorean and slope-intercept. So best memories of 8th grade. Okay, so 8 squared plus 15 squared. Oh, and I did that symbol wrong. I was reminiscing about my 8th grade. I got silly. All right, and equals c squared. And of course, c is equal to x in this one. Okay, so 64 and 15 squared is 225 equals c squared. Let's add those together. So 5 plus 4 is 9. 6 plus 2 is 8. And so 289 equals c squared. Well, we need to take the square root of each of those. Okay. 289, turn my phone sideways, square root 17. 17 equals c, which c equals x. So over here for our answer, it says, what is the value of x? X equals 17. Number 8, a 26-foot ladder is leaning against a wall. The bottom of the ladder is 10 feet from the base of the wall. What is the distance between the ground and the top of the ladder? Okay, so let's draw a picture. So here is our wall. Here is our ladder. And here is the ground, all right? So our ladder is 20, so you need to imagine it. Here's our, okay, so our ladder is 26-foot ladder. Bottom of the ladder is 10 feet from the base of the wall. So we're looking for this value over here. Let's call that B. Okay, so it could be A or B, but we'll call it B. So A squared plus B squared equals C squared. We'll plug in our values. 10 squared plus B equals 26 squared. So I know this is 100. Plus B squared equals 26 times 26 is 676. We're going to subtract 100 from each side. So B squared is 576. Find the square root. $24. And my label is, there it is, feet. So it says, what is the distance between the ground and the top of the ladder? So B equals 24 feet. Okay. Okay. Number 10. Oh, no, erase all that. Okay. Number 9. Number 9. Each unit represents 1 mile on the grid. What is the shortest distance between the school and the park? So we just did this with our distance of a coordinate plane. Let's see here. See if I can draw on this little picture. Hopefully that made it a little easier. Okay, so school and the park. We also have a statue and a mall. Each one of these squares is 1 mile. Looks like it kind of got stretched out funny, so they look almost like rectangles, but just know that they're squares, okay? So we want to go from the school to the park. And of course, the quickest way to do that is right here, take the hypotenuse. So what we're going to do is the statue and the mall, we're not going to worry about. We're going to draw a line straight down from school and straight over from the park. And where these two lines intersect makes a right angle, and that's how we know we can use Pythagorean's theorem. So we want to have, here is A, here is B, and here is C. Okay, so I can just simply count for A from the school. And so that is going to be 1, 2, 3, 4. So that's 4 miles. And from the park, 1, 2, 3. And that's going to equal my C squared. Okay, so 4 squared is 16, plus 3 squared is 9, equals C squared. 16 plus 9 is 25. Square root of both sides. 5 miles equals C. So it says, what is the shortest distance between the school and the park? So it will be this one here, C, which is 5 miles. Otherwise, you would have to walk, let's see, down 4 miles and over 3 miles for a total of 7 miles. So the shortest distance is 5 miles, taking the hypotenuse. Number 10, what is the approximate distance between points 0, 0 and 6, 5? And we need a graph. So I went and copied one real quickly from images. I guess I can just leave that there. Okay, so it says, what is the approximate distance between points 0, 0 and 6, 5? So let's go ahead and graph it. So here is 0, 0. Kind of. Then 6, 5. 1, 2, 3, 4, 5, 6. And we're going to go 5. 1, 2, 3, 4, 5. Okay, so we want to know what is the distance between these. We're going to make it a right triangle so we can use our Pythagorean. Okay, so I want to know this side, which is C. I know that we went up 5. This is 0.65 from the origin. And so right here is 6. So easy. A squared plus B squared equals C squared. Plug in our values. 6 squared plus 5 squared equals C squared. 36 plus 25 equals C squared. And that is going to be 61. Yeah. 61 equals c squared. We'll find the square root of both sides. And so that equals about 7.81 is the approximate distance of C. Good job. Ooh, and here we have 11 and 12. What is the approximate distance between points 4, 3, and 1, -5? Let's see. So first, is it still my clipboard? Yeah, there it is. And 1, -5. Yeah, I think that's big enough. Cool. Okay, so let's go from points 4, 3. So 1, 2, 4, 3 is here. And then we have 1, -5. So over 1 and then down 5. There we go. So we're trying to find the distance between these 2 points. Will be our C. We're going to draw a line down here and over. So we're going to need to count between these to see how far that we've gone. So we'll call this one here A. So we'll say that's a distance of 3. And then let's count up. 1, 2, 3, 4, 5, 6, 7, and 8. And of course, Pythagoreans, a squared plus b squared equals c squared. A squared will be 3, and b is 8. And that equals c squared. 9 plus 64 equals c squared. Okay, so 9 plus 64 is 73 equals c squared. Find the square root of each side. 73, 8.54. It's the approximate length. And it's approximate because that decimal just keeps going. So that's why we put that. There we go. I am unsure why this is 11 and 12. So I don't know if on the benchmark next week that this is going to be covered over 2 problems. Maybe part of it is actually graphing it. It was 11 and then solving it is 12. I don't know. But there it is. Okay, here we go. Number 13. A square with a side length S has the area of 196 centimeters squared. The equation S squared equals 196 shows the area. What is the side length? Awesome, so easy. Okay, so we're going to say S squared equals 196. All we have to do is find the square root of each side, which is 14. So S equals 14. Here's our label. Because we did a square root, it's no longer squared. It's simply 14 centimeters. Liked that one. That one was easy. Okay. Here we go. 14, 15, and 16. This says classify the following as a perfect square, perfect cube, or both. So perfect square is a number which comes out to a whole number. So like 36 is a perfect square because the square root of that would be 6. 6 times 6 is a whole number. It's not a fraction or a decimal. Same thing happens with cube root. So I'm thinking of 27. 27, the cube root of 27 is 3 because 3 times 3 times 3 equals 27. They're both perfect. We call them perfect because they're nice and neat. No decimal or fraction remaining. Okay, so let's see here. Number 14, we'll do for 216. Okay, so first, let's see what the square root is. Square root of 216. All I'm going to do is use my calculator. Square root, 14.698. Not a perfect square. So now let's do cube root. So we'll go back in there, 216 cube root, 6 equals 6, since 6 times 6, that's 36, times 6 equals 216. So 216 is a perfect cube. All right, there you go. If you're looking for perfection in this world, perfect squares and cubes. All right, number 15. We have 729. Let's go ahead and we'll just do the square root first again. 729. Square root is 27. So, and that would be since 27 times 27 equals 729. So yes, that is a perfect square. Could it be a perfect square root? I'm sorry, cube root. We just did square root. All right, 729. Cube root is 9. You see it? Awesome. 9 since 9 times 9 times 9 equals 729. So look at that one. It is also a perfect cube. Very cool. Okay, I'm going to have to delete the rest of all of this to do 196 for number 16. Okay, clear. So number 16, we want to know about the number 196. Square root. 196. Here. Square root is 14. Woohoo! Perfect square. Okay, so since 14 times 14 equals 196, that is a perfect square. Okay, so let's see about a cube root. So on my calculator, 196 cube root, nope, 5.8 and a whole bunch of numbers. So it is not, not a perfect cube. I guess I could have written down the answer. It equals 5.808, and it continues. Okay, so it is a perfect square, not a perfect cube. We can't all be totally perfect. And that brings us to 17 through 20. So there's 4 problems here. Indicate if rational or irrational and why. Okay. So for this, rational and irrational, if you're not sure, look what I did. I went and pulled from my math notes on rational and irrational numbers, and all you had to do was put this in your folder. You didn't even have to write it down if you didn't want to. What a great resource. All right. So let's see. I don't know. You can read it. I can't really read it while I'm holding it because on mine it's backwards. Let's see here. Rational numbers can be written as a ratio of 2 integers. Okay, so you can see an example is a square root. Let's see here. The example here is 2 and 0.3 and negative 1600. So if you remember, for it to be rational, it has to be a perfect square. It has to be, the decimal has to end or terminate, or it has to be a repeating number, like 1/3. Okay, so the irrational numbers cannot be written as a ratio of 2 integers. And so it says all square roots except for perfect squares and all cube roots except for perfect cubes are irrational. And then the other note is that so is pi. Okay, pi is so irrational. So let's take a look and see what these are. Okay, so this first one, easy because I'm going to do green. So for number 17, square root of 5. Well, I can look at that and I already know that it's irrational because it's not a perfect square. Okay, so square root of 4, that's a perfect square, it'd be 2. Or if I went to 9, which would be 3 squared. So this is irrational. Because it's not a perfect square. Okay. Number 18. We are looking at the square root of 4/36. Okay, square root of 4/36. So we're going to actually simplify that. Okay, so this simplifies to the square root of 4 over square root of 36. I know those are both perfect squares, so that gives us the ratio 2/6. And of course, we can then simplify that down to 1/3. So I can write it as a ratio. And then, of course, I know that that is a repeating decimal. And yes, repeating decimals are rational, which we could make it a ratio. So yes, rational. Okay, that's a pretty color. I should use that one more. And my favorite. Let's see here. 19. We are going to do pi. We already know it's not rational because the number goes rational. All right, because the number just continues on forever. Okay, so it does not terminate or end. 3 letters, much better. Does not end or repeat because we know that is 3.141 blah, 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 blah. So irrational. And number 20, square root of 49. Well, the square root of 49 is 7. So yes, that is rational because it is a perfect square. Okay, 17, 18, 19, and 20. Here we go. Solve the expression that has a value between 0 and 1. So what I'm seeing here, why don't I have my glasses again? Oh, it's so much better. All right. So what I'm seeing here are 3 different equations I need to simplify with exponents. Okay, so great. This is fresh in my mind because we just did this on part 1 this week. So let's start with A. Three to the 4th power times 3 to the negative 3rd. When I'm multiplying exponents, then when I'm multiplying the same base with an exponent, then I'm going to add the exponents together. Okay, so that one equals 3 times 4, or to the 4th power, plus negative 3. So that equals 3 to the 1st power, which of course is itself. Okay. So it says solve the expression that has a value. Okay, so that value is not between 0 and 1. I think that's what it's asking. Okay, get another color here. B is a division problem. 8 squared over 8 to the negative 3rd. Oh, I get what we're saying here. Oops. So we are going to be subtracting these exponents. Can you tell that's a negative 3rd? Yeah. All right. So this is 8 to the 2 minus negative 3. So we're going to end up adding 2 negatives. Becomes a positive. So that equals 8 to the 5th. Which 8 to the 5th, that is going to be a lot more than between 0 and 1. So no on that one. Okay, and then C. Uh, 5 to the negative 6th times 5 to the 4th. So we're going to add those. 5 to the negative 6 plus 4. So that is 5 to the negative 2nd. So yes, that one, if we were to look at that one, so these are the ones that are crazy. With that negative exponent, we can actually get that negative out of there by making it a fraction. So I want you to think about this. We would move this decimal 2 places this way, okay? Or as a fraction, we would make that 1 over 5 squared. Okay, by putting it in the denominator, that's where that negative is. So that gives me 1/25. Is that between, our question was, between 0 and 1? Yes. There it is. This one here, no. This one here, no. My same one. There it goes. Okay, evaluate, answer in scientific notation. Okay, so looking at this, I see that with the parentheses, that clues me in that they're being multiplied times each other. So I'm going to add the exponents from the 10th. Okay, so this is the same as 4 times 3. Pull those out. times, that's an X, 10 to the 5 plus 3. Simplify. 12 times 10 to the 8th. Let's wrote 5 again, so that's 10 to the 8th. But look at the 12 is too big. It has to be between 0 and 10. So we need to move this decimal over 1. And because we're going from a bigger number to a smaller number, we're going to add 1 exponent here. So our answer is 1.2 times 10 to the 9th. Check my answer. A-okay. There we go. All right. Okay, number 23. One crate holds 1.5 times 10 to the second boxes of candy. If there are 7.5 times 10 to the 5th boxes of candy, how many crates are needed? So what I want to first say is that's a lot of candy, right? So for this one here, this 1.5, you're going to take that decimal and move it 2 places. So that is for 150 boxes of candy. And then for this other one here, holy moly, we're going to move that decimal 5 places. 1, 2, 3, 4, 5 means that is 75. 1, 2, 3, 4 zeros. Okay, 750,000 boxes of candy. So kind of a real life application so you can see why do we use a scientific notation. This is a silly example, but it just shows you how it makes those huge numbers more workable. So just imagine, if you put things into the 100,000, millions, billions, that's why you use the scientific notation. Okay, so let's solve this. One crate holds 1.5 times 10 squared. Okay, so that's for one crate. But we have 7.5 times 10 to the 5th. Okay, so what we need to do is divide the amount of candy we have divided by how much goes in each crate, and that's going to tell us how many crates that we need. Okay, so we are going to say 1.5 times 10 squared divided by 7.5 times 10 to the 5th. Okay, so we'll go 1.5 divided by 7.5. And that equals 0.2. Times 10 to the 2. Rewrite that one. Minus 5. Okay, or plus a negative 5. Okay, so equals 0.2 times 10. 2 plus negative 5 is going to be right here. Well, this 0.2 is not between 1 and 10, so I know that I need to move that decimal. Oh, wait. I totally did this problem wrong. Sorry. All right. If I had editing capabilities on these videos, I would rewind, but I don't. Oh, well, mistake. Here's what I did wrong. I divided the wrong thing by the wrong thing, and I think I said it correctly, but then I totally wrote it wrong. So some of you caught my mistake. Some of you are like, gotta erase it. No, you don't. Just cross it out and continue your problem farther down your page. All right. Glad I figured it out now. All righty. So I want to do the number of boxes of candy divided by how many go in a crate. Okay. 7.5 times 10 to the 5th is how much candy I have, divided by how many boxes will fit into one crate. There, makes a lot more sense. Okay. So now 7.5. I was thinking 0.2 crates. That's not much. All right. 7.5 divided by 1.5 makes much more sense, is 5 times 10 to the 5th minus 2. 5 times 10 to the 3rd. Okay, so that's our answer. But because I worked out the scientific notation, and it just makes me curious because I like candy, if I were to put this into standard notation, I would move my decimal 3 spots. So that would go, 1, 2, 3. I'm going to need this many crates. Okay, but the scientific notation is your answer. All right, a lot of crates, a lot of candy. Yay, write the equation of the line. This is what we have focused on the most this year, but it just seems like it was so long ago now. So we want to write an equation of the line. And of course, our slope-intercept form would be y equals mx plus b, where m is slope and b is the y-intercept. And what that means is that's where the line crosses the y-axis, which is this one here. Okay, so when x equals 0, then b is wherever it crosses. So y-intercept. You can read that. Okay, so what's my b? It's right here. It passes through the origin. So I already know that my b is 0. So now I need to find my slope. Oops, dropped my stylus. My slope is rise over run. Well, how convenient. Here it is. I see that this point here has a rise of 1, 2, 3, 4, 5. And look at this. It has a run of 5. So I know that my slope equals 5 over 5, which is 1. And then, of course, my b-intercept is 0. Oh my goodness, 2 mistakes in a row. Look at this. Here's why. Can't believe it. All right. Looking at my chart, it does not have a rise of 5. It has it of 25. Oh, man. All right. So 25 over 5 means that I have a slope of 5. So y equals 5x plus 0. Of course, that is the same as y equals 5x. That's the equation for that line. All right, number 25. Whew, we are past halfway, thank goodness, because I'm starting to make mistakes. Told you it was pretty brutal, huh? Or did I say gnarly? They're both. All right, 25. How many solutions does the following equation have? Okay, so I want to remind you, we can have no solution, we can have one solution, or we can have infinitive solutions, okay? So what we need to do is solve this equation, simplify it, and see how many solutions. Okay, so I'm going to rewrite so it is bigger because, my handwriting's huge with this stylus. All right, so I have 8x plus 6 equals 6 times 4/3 x plus 2. Okay, so we're going to keep this one here. And we're going to distribute the 6 over both of these. So 6 times 4 is 24/3 x plus 12. Well, 8x plus 6, that one continues. 24 divided by 3 is 8, so 8x plus 12. Well, look at this. Let's get rid of those 8. So if I subtract, or 8 x's, I guess, 8x from both sides, then that leaves me with 6 and 12, and they are not equal. 6 does not equal 12, so that means no solution for you. All right. Come on. There it goes. Number 26. A system of two linear equations has no solution. One equation is x minus 3y equals 6. Okay, so if two linear equations, that means they're straight lines, have no solution. A solution is where two lines intersect. It would be right here, right where the x is. So if there's no solution, it means that they are parallel lines. Okay, parallel lines. So it's telling us what one of them is. And it says what could be the other. And so what we're going to do is we're going to take this first equation and put it into slope-intercept form, which is y equals mx plus b. And the reason we're going to do that is we're going to find out what the slope is. So if they are parallel, they have to have the same slope because they never intersect, okay? They go on forever and ever, and they never intersect. So that means they have the same slope, okay? So we need the x on the other side because, of course, let me write it up here. Y equals mx plus b. So we will subtract x from both sides. And negative 3y equals, and to put it into this form, I'm going to put negative x plus my 6. Okay, so now negative 3y equals negative x plus 6. I need to get y by itself because that is my slope-intercept form. So next thing I need to get rid of is that negative 3. So I'm going to divide everything by negative 3. Equal opportunity. Okay, so that gives me y equals, so a negative by a negative turns to a positive. So that's going to be, and this is a 1 here, so that gives me positive 1/3 x. That's my slope. And then 6 divided by negative 3 is going to make that negative, plus negative 2. There's my y-intercept. So I know that this parallel line cannot go through the same y-intercept because they don't share any points that are the same. So a possible, it says what could be the other. Here's the first one. The other one could be y equals, it's going to have the same slope, but a different y-intercept. So let's just make it, how about positive? Well, I was going to say positive 2, but I don't know. Is that confusing? I don't know. We're going to do it. Okay, so it's on the other side of the x-axis. So those are two lines that are parallel. They never intersect, and so they have no solution. Okay. Number 27, draw a graph that is a function and a graph that is not a function. Okay, so a function has one input or one output for every input. Okay, and so with that, you can have a horizontal line that has a slope of 0, but you can never have a vertical line because that means the rise would be infinite, but the run would be 0, and any fraction that has 0 in the denominator is undefined. So that would not be a function. So our function, here's our function. There we go. Okay, here is our x and our y. So our function could be something like this. Okay, it's not a straight line. We didn't say it was linear, but it's a function. But if we did something like this and did the same thing, but then went straight up, that is not a function. And that's because of the vertical line right here. Okay. Vertical line is a no-no. Okay, so draw a graph that is a function and a graph that is not a function. There you go. (28) If two functions have the same rate of change, and here's your table, one is represented by the table, what is the slope of the other function? Okay, so we have two words here. We have rate of change. So it says if this one has this rate of change, what is the slope of the other function? Rate of change is the slope. So if they are the same between these two functions, then we can simply find the rate of change or slope here, and that will be the slope. Okay, so when we do slope is represented by m, and it's going to be the change in y over the change in x. Okay, so y, remember, is the rise over run. Okay, and so if you think about that on your graph, rise is the y because it goes up and down, up and down. X is the run because that one goes left and right. Okay, so the way that we say the change in y is we're going to say y2 minus y1 over the change in x, and that will be x2 minus x1. Okay, so let's just simply pick some coordinates. So let's go right here. This can be, use this one and this one. Okay, so we're going to do our change in y. Remember, y is on the bottom, so it doesn't even matter. So this could be 1 and 2. So y2 is going to be negative 3 minus 3 over, and make sure we go in the same order. So we're going to go from 2 to 1. So over x1, or I'm sorry, x2 minus there. Okay, so we need to do a couple things. First, let's add the opposite. So let's say we're going to add the opposite. There it goes. Equals negative 3 plus negative 3 is negative 6. 1 plus a negative 3 is negative 2. Negative divided by a negative makes it a positive. So that means our slope is 3. So it says, what is the slope of the other function? There it is. M equals 3. Okay. All right. Number 29. What does the graph of a linear function look like? Write an equation that does not represent a linear function. So a linear function is going to be a straight line. And we talked about this a couple problems ago. It can be a horizontal line. So it can be a horizontal line. And with this, the slope is 0 because it doesn't go uphill or downhill, but it cannot be a vertical line. Okay, so it can't be vertical because we can't have a run of 0. It's just undefined. An equation that does not represent a linear function, so linear means it's a straight line, is it can't be a parabola. A parabola is something like this, and that's represented usually by something squared. So let's see here. If I were to write the equation y equals 2x squared plus 3. This is not a linear function, and it's because that x is squared makes a parabola. And you will be learning about those in graphing notes in high school. Okay? And you'll be like, she said this would happen, and it did. Okay, that's it. Number 30, write the equation of a line. Awesome, we can do this one. Equation of a line, of course, is y equals mx plus b. So m is slope, so we need to find out what m is and what b is. We leave x and y because those are the coordinates that we plug in that get graphed on the graph paper. Okay, so let's do our slope first. M equals rise over run. So let's see, if we were to go from this point to this point, first of all, our rise actually goes down 3. 1, 2, 3. So it goes down 3. It's represented by the negative. Lets me know it's going downhill, which it is because we read from left to right. And then we are going to run 1, 2, 3. We run 3, which means we have a slope of -1. Now I need to see what is my y-intercept. Y-intercept is when x equals 0. So when x is 0, here it is, and y is 1. So my b equals 1. So if I plug in those values, the equation of this line is y equals -1x plus 1. Okay. Now, I've always put in that 1 just so we help remember that that's our slope, but it would be the same as y equals -x plus 1. There's your equation of the line. And oopsies. Oh. There we go. Not the right one. Write the equation 30. There we go. 31. Let's see here. The question is, between what times does the elevation increase the fastest? So increase the fastest lets me know that it is looking for the greatest rate of change or the steepest slope. So I can visually look at this and see that right here. So here's 8 o'clock. That means here is 9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock. I can tell that between 9 and 10, it's the steepest. Okay, so that's where my increase is the fastest. We go rise over run. So it increases 100. Let's see, it increases, that's my sub in, by 100. And it goes, so because it goes from 50 to 150. And it does that, so that's feet, in only 1 hour's time. 1 hour. So my rate of change would be 100 feet per hour. Okay, so that's where my greatest rate of change is. And we would, but it says at what times does the elevation increase the fastest? So my answer is going to say between 9 and 10. Okay, there it goes, rate of change. Number 32. Okay, number 32. Square ABCD has side lengths of 3 inches. It is rotated at 90 degrees counterclockwise about the origin, then translated, so rotated and then translated 2 units down. What is the length of side CD? Okay, so this one, don't let it trick you. It's a square, ABCD, hip to be square, and each side has a length of 3. If it's a square, then all 4 sides have that length. It never says dilated. Okay, so dilation is when you get bigger or smaller. So the side length never changes. Side length is 3 inches. Okay, describe the sequence of transformation that maps figure A onto figure B. All right, and because I can, I'm going to go ahead and enlarge this. Ugh, that's not my glasses, right? All right. Oh, they did. Oh, that's pretty blurry now. That's all right. Okay, so what did figure A do to become figure B? Okay, so let's take a look. The first thing is it's going to rotate around the origin. So, of course, this is the origin here. And so if we were to rotate that up, it would put it, let's see here. Yeah. Here and there. So there is transformation 1. Then if I look at it, they look like mirror images between here and here. So I am then going to reflect across the y-axis. So that brings us to here. Okay, so it's a mirror image. Then I'm going to translate it, which means just scooch it. So then it's going to be translated. So how do we write down all of those things? So first, we rotated. Oh, rotate. My goodness, can you tell I'm so tired? This video is taking hours. That's okay. All right, so first I'm going to rotate, and it rotated clockwise. Oh, I think that I need to say 90 degrees first. Where is it? Yes, I'm going to do that first. Okay, so rotate 90 degrees. Oh my goodness. 90 degrees clockwise. And we need to put about the origin. Okay, so about the origin. Okay, that's what we did first. Second thing we did is we reflected. Reflect across y-axis, because of course this one here is x and this one is y. Then we translate, and we went to the right 1 unit. Okay, so it took 3 steps in our translation to get figure A to figure B. (34) If triangle MNP is dilated, well, there's our word, dilated, so it's either going to get bigger or smaller by a factor of 4, what would be the coordinates of the image of point P? Okay, so it just wants to know about point P. We could do all of them. We could even draw them on the graph, but because this question is specific and only wants coordinates of the image of point P, almost looks like a P, that's what we're going to do. Okay, so dilated by a factor of 4, that means we're going to multiply 4 times whatever x is and whatever y is. Okay, so I can look here and I know that P is point 1, 2, 3, 2. Okay, so I'm simply going to go 3 times 4 and 2 times 4, which that's going to give me my next point P. P1 is 12, 8. Right, and that's it. Number 35. 2 polygons are not congruent, but they're similar. So congruent is the same, but they're similar. What transformation must be used to verify that they are similar? And explain. Okay, so for this, it's what we were just talking about dilations. So when we, what was that, 2 problems ago, when we moved triangle A to become triangle B, we rotated it, we did a mirror image, and then we translated it. Okay, and those 2 triangles were congruent. So if you were to overlap them over each other, they would cover completely because they are the same. Now, to be similar, that means that they are probably the same shape, but they are not the exact same size. Okay, so an easy example would say, look at these 2 circles, kind of circles. Okay, they're similar, they're both circles, but they're not congruent. They are not the same. So the question is, what transformation must be used to verify that they are similar? And the only one that deals with size is dilation. Dilation. So in class, remember what we talked about for dilation were your eyes, your pupils. And when you go to the eye doctor and they dilate them, they put these drops in your eyes and they feel all like puffy and fuzzy. And if you were to look at your pupil, it is actually dilated, which means it's grown bigger. It's still a circle, but it's bigger. And what that does is that allows in more light so that the eye doctor can look in your eyes. And that's why your eyes are so sensitive when you leave the eye doctors. You have to wear your sunglasses until it goes back to normal. So, in fact, look at this. These could be your pupils right here. All right. So dilation's the only one that has to do with size. All right. Oops. Delete. Ooh, we're getting there. There we go. 36 through, I think that's 39. Find the volume of the cone. What that's, I think is what it's saying is that on the benchmark that we will do next week, numbers 36 through 39 on that test will have to do with volume of a cone. For us, we just need to find it for the volume of one cone. So I want to remind you, of course, I think, although my paper's from the first video, you can go back to your notes or your red resource. Where are ya? There you go. Here's the volume of a cone. So it's going to be 1/3 base times height. And of course, the base is a circle, and it's all about that base. So that's going to be pi r squared. So here we go. Our volume of a cone, the formula is 1/3 base times height, where our base is a circle, so it is pi r squared times height. It's that squared because it's the area, surface area of that base, and then it's multiplied times the height. So let's plug in our values. 1/3 pi. Right here, you'll see that it is pointing to the diameter. Diameter is all the way across. Radius is half that, so that means our radius is 3 times a height of 3. So, this is nice. We can simplify here. 1/3 of 3, or 3 divided by 3, is going to be 1. So we got rid of that, which leaves us with 9 times pi, because 3 squared is 9. So 9 times pi. Let's go ahead and use the calculator. 9 times 3.141 equals 28.269. Label is meters cubed because it's volume. In our assignments, we've been rounding that to the nearest hundredth, so that would be 28.27 meters cubed. But there is the volume of a cone. You just need to remember the formula. It's right here. Okay. Okay. And here we go. Look at 40, 40, and 40. This is all number 40. Oh, vacation. Sounds wonderful, right? Summer's coming up. Don't know if anybody will be doing vacationing this year. Vacation. The table shows, I'm going to definitely need the glasses. All right. Vacation. The table shows the distance you travel over a 6-hour period. Long time to be in the car, if you ask me. Make a scatter plot of the data. Draw a line of best fit. Write an equation of the line of best fit, and then predict the distance you will travel in 7 hours. So this chart here has that you're traveling for 6 hours, and it's a scatter plot. And what that means is that every plot, so each of these are not going to be on your linear equation. It's not going to be on the line, but you're going to find that line of best fit. And it really just finds an overall average for your rate of change. And from that, then you can figure out and predict how far you'll travel in 7 hours. Okay, so let's see here. Yeah, so I thought this one's labeled higher numbers, but that one, I guess it's ABC, whatever. Okay, so we went to do a scatter plot of the data. Okay, and I went and I grabbed a graph, picture of a graph. There we go. So that we could plot this. And I think I'll leave it right there. That works for me. Okay, so first we need to do a scatter plot where we're going. Oh, maybe I want to move that because my head. I need to go up to, how far away are we going? A distance of 344. There. Okay. So maybe if I actually shrink that up. All right. Sorry, guys. Okay. I think that helps. Okay. So what I need to do is I am going to label this chart, and I'm going to have the origin be right here, which is going to be 0, 0. And so let's see here. That is my x-axis. This is my hours. This right here is my y-axis. And that is going to be my distance, which is in miles. Okay, distance in miles. Okay, and so now I'm going to erase those lines because those are just super squiggly, but just so you know, this bottom one here, I know what I can do. I'm just going to put a text box over that so I can make it a smooth bottom. That didn't work. Delete that thing. Get out of there. All right, undo, whatever. New one. Let's see if I can do it better. Yes, okay. Where'd it go? Okay, whatever. Move it up, and then I'm going to give it, there we go, it's like white out. Okay, that works. Okay, so now I know that the total hours that I've gone so far is 6. So I want to make sure that I can go 6 hours, and I'm predicting 7. So I'm just going to skip every 2, and let's see if I can write small enough here. So this is going to be 1 hour, 2, 3, 4, 5, 6, 7, and 8. And so I'm just skipping every other line there. And then I'm going to have each of these squares going up be 25. So that means this first one is 25. Then up 4, 1, 2, 3, 4 is going to be 100. Then another, it's there, 1, 2, 3, 4. There is 200. 1, 2, 3, 4, 300. 1, 2, 3, 400. Oh, nuts. Oh, no, that's fine because we've only gone 344. I don't know what I was thinking. So 100, 200, 300, 400. That is fine. Okay. So now we're going to do our scatter plot. And I apologize. It's so messy. It's really hard for me to do, but hopefully on your paper, you're able to do a better job. Let's get green here. So our different points. So our first, they're going to come from right here. Okay. So our hours is our run, and then our distance is our rise. Okay. So in 1 hour, we went 62 miles. So right about here, because I know 2 units up, it's going to be 53 is 75. So it's right in there. In 2 hours, I went 123. So there's 123. 3 hours, 188. Okay. 4 hours, 228. 4 goes to 200. What is it? 28. So just barely above right there. And then I have 5 hours is 280. 6 hours, 344. Okay. So you can see they're not quite in a line, but they're pretty close. And it's going in the same pretty constant speed in that direction. That's why we can do a linear line. And the line is going to go through the origin because in 0 hours, we went 0 miles. Okay, so now we're going to draw a line through there. And I don't really have a straight edge that works for this. So we'll try. Let's see here. So it's hard because it's a touch screen computer. Oh, there's my hand. Let's see if I can get this kind of straight. From 0. Oh, look that's where my knuckle was touching. It didn't work. Okay, let's try again. Pretty good. And of course, with the fat tip, it goes through almost like every point, which is fine because it is our estimated rate of change. Whew. All right, so it's pretty good. So now, let's see here. So we did a scatter plot right here. Done. Now draw a line of best fit. Done. Write an equation of the line of the best fit. Okay, so let's look and see. It looks like, where is a pretty good point that it goes through, where it goes through? I think right here at, it's like 4.5, I guess. I'm getting a new color. Because I want to find our slope. Okay, so I'm trying to find where it goes pretty well, which I think 4.5 right here is the point that I want to use. Okay, even though it's kind of funny. So rise over run. Okay, so my rise to this line here is, here's 200, 225, so 250. So that's going to be 250 miles. And that comes down to here, 4.5 hours over 4.5. Okay, so that is my slope. And I'm actually going to simplify it and just make it a decimal. So 250 divided by 4.5 is going to give me a slope of about, look at 55.55555. So, and put 55.55. Okay. And so what that's telling me is miles per hour. So that's how far I'm driving. So driving quite conservatively under that speed limit. And it wants to know how far I will go in 7 hours. Okay. So my equation of the line is y equals mx plus b. Well, I know my b is a 0, so y equals 55.55 x. Okay, well, my x is the amount of time, and I want to know in 7 hours, so I just have to multiply this, and so I want to know the distance, that's my y. So 55.55 times 7 hours, I'm going to go about 388.8 miles. So I'm going to round that up to 9.89 miles. So my distance is going to be 388.89 miles. And that's how far we should have traveled on our vacation in 7 hours. All right? Kind of fun, right? Oh, come on. Okay, so look at this. This is numbers 41 to 47. Ooh. Oh man, we're gonna have to figure out what this chart says. Okay, so 41 through 47, it says you randomly survey students between the ages of 12 and 17 about whether they ride the bus to school in the morning, and the results are shown in the tally sheets. Okay, so we are going to complete the table. Oh man, let's see if we can enlarge that and make out what it says in each of those. Good news is that to complete the table, it's pretty easy. So let's see if that one or this paper here. So student, let's see here. This one, this box here says students. Okay, and I think this says rides the bus, does ride the bus. So we're going to say bus. And then this bottom one says does not ride the bus. So we're going to say no bus. Okay, so then at the top, this is age. Okay, and so we know that it's surveyed between 12 and 17. Oh, look, we can tell barely. 12 to 13, 14 and 15, and then 16 to 17. I made that one funny. All right, we figured it out. Cool. Okay. 16 to 17. Okay, and we simply want to fill this total out. All we have to do is add these numbers up, and we're going to have our answer. Okay, so for the students that ride the bus, all ages is going to be 24 plus 12 plus 14, and that gives us 24 plus 12 plus 14, total of 50 students that ride the bus. The number of students that don't ride the bus is 16 plus 13 plus 21. We're going to add it this way. So the students that do not ride the bus, well, look at that, is also 50. Okay, so that means that we have a total number of students. It's 100. Okay, and so now we want to know, have it broken up by age group. Okay, so the total number of students that were surveyed that were between the ages of 12 and 13, it's going to be 24 plus 16. 24 plus 6 is 30, plus 10 is 40. 12 plus 13 is 25. 14 plus 21 is 35. 25 plus 35 is 60. 60 plus 40 is 100. So we are finished. Table completed. Okay. Cool. So these data tables are just categorizing and kind of organizing data. So when you complete those, that's what you're doing. And that was to 47, I believe. One more problem. Oh my goodness, could it possibly be? Let's see here. There it is. 48. Proportional relationships. Yay. So apples cost $2 per pound. Make a graph that represents this proportional relationship. All right, let's see if the graph is still on my clipboard. I can just paste it. It's going to be there. Yippee skippy. Okay. And I do want a little bit bigger. And I can really Oh yeah, let's enlarge it. Let's help me out. Okay, so we're going to start at the origin because for $0, we can buy 0 pounds. So let's make that be right here is 0, 0. Okay, there's our point. Okay, so $2 per pound. So let's have our number of pounds down here. Here's 1 pound. Here's 1. Here's 2. 3. You'll see I'm skipping, making them big squares. Help out my fat writing. And then we're going to go up. Cost is $2 per pound. So here is $1, $2, $3, $4, $5, $6. Okay, and these are the, down here is the pounds or the lbs. Okay, so $2 per pound. So for 1 pound, I want a different color. For 1 pound, it's going to be $2. There it is. 2 pounds, it will be $4. 3 pounds will be $6. Okay, so here is our linear relationship. It goes from 0 and it increases. There is our graph. Yeah, so $2 per pound, that lets me know that my rate of change or my slope is 2 because that's 2 to 1. And my y-intercept, of course, is 0. We started in the origin. So my equation for this line or this proportional relationship would be y equals 2x. Okay, and that brings us to the end of benchmark 7 review. Oh, we did it. I hope you were able to understand and pause and just really understand these concepts. It will be very, very similar to these same problems that will be on the benchmark test next week. Of course, it's not a traditional assessment or test where it's going to have that affect your grade. It is for completion. But I hope you hung in there and got it done. I know distance learning is hard, and I just want to commend you for sticking at it. And it is important. Right now, it's cool because you're in charge of your learning and where you're going to continue and start next year in high school. Okay, so I hope you have a fabulous week. I miss you. And all you do, remember who you are, remember what you stand for, and lead by example. Bye, guys.